So yeah, third talk of the session is Mahsa Derakhshan, who's going to be talking about security games. Sorry, all.
Thank you. So I'm going to talk about spatio-temporal security games beyond one dimension. It's a joint work with Soheil Behnezhad, Mohammadtaghi, Hajiaghayi, and Saeed Seddighin. So spatio-temporal security games are about protecting a set of valuable moving targets. It's a game. It's a two-player game between an attacker and a defender, and an attacker seeks to attack these valuable targets, and the defender has a set of patrols that can move to protect these targets. It has many real-world applications. For example, protecting vessels from pirate activity, wildlife protection, protecting urban transit systems, and so on. In all these scenarios, there are some valuable targets that are moving and need to be protected from possible attacks. So as I mentioned, it's a two-player game, and it's constant sum. And players are attacker and defender. There are moving weighted targets, and the movement of targets are known in prior for both players. So, and the defender has k-homogeneous resources, which we call patrols. We assume that both time and space are discretized, which means that resources can only land on discretized positions, and also time is discretized into t different time points. So I first explain the one-dimensional case, and then talk about how we generalize it. In the one-dimensional space, patrols have limited speed, which means a patrol can move from position M1 to M2 in single time point if the difference between M1 and M2 is at most delta. Also, patrols have protection range, which means if a patrol is protecting a target, the distance between them is at most r. This is the visualization of one-dimensional space, and these are two patrol paths. This is time, and this is our space, which is repeated the number of times. And this gray area is a protection range of these patrol paths, and the targets are protected if and only if they are in this gray area. So it's not this one-dimensional case is not the case for the real-life applications, and real-life domains are more complicated than this. So what we do is to model the space by a graph G, which with the vertex set V and edges E. For any special position, we have a vertex in set V, and we assume that patrols and targets can only be positioned on the vertices. Also, edges of this graph show how how patrols can move. But targets are not restricted. They can move. They're not restricted to edges. So because of that, we treat these targets of different time points as n totally different objects. Also, the protection is such that a target can be protected by a patrol if their distance is at most r, the number of edges, the shortest path between them. The strategy of the attacker is to choose a target at one time and attack that. Also, the defender's strategy is a valid patrol scheduling. An attack is successful if at the time of the attack the target is not protected. And the utility of the attacker is equal to the weight of the target if the attack is successful, and 0 other ways. the goal here, the goal is to find the maximum strategy of the defender, but as we see here, the number of pure strategies of the defender is not polynomial in the input size, even even in just one time point. So we cannot use classical LP methods to solve this problem. This problem, for the one-dimensional case, it has been studied extensively. There were some algorithms for special cases, and finally, an algorithm for the one-dimensional case in general by Behnezhad et al. And it's also proven that if in the one-dimensional case patrols have acceleration, then it's not the problem is NP-hard, and there's no polynomial time algorithm for that. Our results here is that for the general case, we give a hardness result even for the one single time point, and we give an approximation algorithm. We give an approximation algorithm that gives 1 minus epsilon approximation using up to log of 1 over epsilon times more patrols. Also, our approach works for the one-dimensional case, and it gives an exact polynomial time algorithm. It also handles multiple attacks. Sorry. So we start with the classic LP method. In this LP, okay. We represent the pure strategies of the defender by vectors of length A. A is the number of targets. So S of A is the protection of target A by this strategy. And so here, this set is the set of pure strategies of the defender, and P sub S is the probability of playing this strategy in the mixed strategy. So here, the number of variables is exponential in the input size because this set is exponential, has exponential size. So we cannot solve this linear program. So because of that, we write the dual form of that, in which the number of constraints are exponential, but the number of variables are polynomial. In the dual form, the vector y denotes the mixed strategy of the defender, which means the y of I represents the protection of target I in this mixed strategy. So to solve the dual form of the graph, dual form of the LP, we use Ellipsoid method. For that, we need an algorithm for the separating oracle that for any assignment of variables either decides that all the constraints are satisfied or reports a violating constraints. Here, the first three set of constraints are polynomially many constraints. And the only set that we care about, the only set of constraints, is this last one, that are exponentially many. We define this problem, which we call the best response problem, and we use that for solving the separation oracle. In this problem, given vector h, we want to find a pure strategy of the defender that maximizes S.h. This would be just a combinatorial problem that we can look at this vector h just like as a weight assignment to the targets, and we want to find the pure strategy that collects the maximum weight. So if we have the solution to this problem, we can use it here and solve the LP and therefore the main problem. So here, solving the best response is equal to solving the separator oracle, and So I first need to define this temporal graph, which is a directed graph, and it contains a vertex for any pair of spatial position and time. And the edges of this graph represent how patrols can move. The columns are a number of time points, and rows here are spatial positions. This is just a representation for the one-dimensional case because it's simpler to represent. And any patrol path here maps to a path in this graph. For example, these are two patrol paths in this graph. The overall, okay, I'll just focus on solving the best response problem. For that, the overall idea is to write a linear program and find a fractional solution for that, like the same ideas that the previous work had. Yes, we find the fractional solution, and then we use LP rounding techniques to find an integral solution based off that. So the fractional solution, okay, what do I mean by the fractional solution? In this solution, we assume that patrols can move fractionally. For example, one half of the patrol can move from a path, and the other half moves from another path. We can represent any fractional solution here by a network flow on the temporal graph. So this is the linear program that finds a fractional solution. This set of constraints are just the classical LP constraints, classical fellow constraints. And this last one is to maximize the coverage. After finding the fractional solution, we give two different LP rounding methods for the general case and the one-dimensional case. Okay, the DBR problem on general graphs is NP-hard. We give a reduction from the dominating set problem, and because of that, it's even hard to approximate within this factor. So we need to give some approximation algorithms for that. We define an alpha-beta approximation solution, a solution that achieves alpha fraction of the optimal solution by using up to beta times more patrols. And okay, now I'm just trying to find the solutions for the best response problem. But when it comes to approximation solutions, we also need to prove that any alpha-beta approximation of the best response problem also gives an alpha-beta approximation of the actual game. And we prove it in the paper. In the LP rounding method that we give here, it's in such a way that the probability of each target being protected is 1 minus 1 over e fraction of its fractional protection. So because of that, we can give this approximation solution, which if we set epsilon equal to 1 over e, it gives a matching upper bound to for the hardness that we have. Okay, now for the one-dimensional case. Here we give an exact solution. The first step is to choose a fractional number sigma between 0 and 1. Then for any t and k, t is time and k is the number of patrols, we choose the topmost vertex in the temporal graph that has k plus sigma amount of flow passing through vertices below it. For example, here, the amount of flow passing through here is sigma, here sigma. And then we claim that among these chosen vertices, the set of topmost vertices form a valid patrol path. For example, these are valid patrol paths. And we prove this using the fellow conditions that we had in our LP. Also, we show that the probability of each target being protected is equal to its fractional solution. to its fractional protection. And because of that, the integrality gap of this rounding technique is 1. And that's it. And for the future work, I think there are some possible works to see if for online or stochastic variants where the trajectories of patrols are not given as the input, it's possible to give polynomial time algorithms or improve the approximation factor for special cases, for example, 2-dimensional or even grids. Questions?
Are there any questions? Yes, please.
So you mentioned that alpha beta approximation for the nuclear alpha can be transferred to the alpha beta approximation for the original.
Excuse me, can you please repeat that?
So you mentioned that if you have an alpha beta approximation for the EV alpha,
Yes.
you can transfer it to alpha beta approximation for the original.
Yes.
So I'm wondering whether your reduction depends on the particular structure of this problem, or your reduction actually works in general for like any structure.
I believe that it works in general. What do you mean by the specific?
Like in this particular domain, you have this spatio-temporal structure or whatever.
Oh, it's for whatever security game.
Or whatever.
Yeah.
Did you go through the Ellipsoid method?
Yes, yes. Yeah. Any other questions?
Any other question? Right. Thanks for the speakers of the session.
Thank you.